Okay, welcome to the online worked examples for week 2. So the first problem we're going to do is chapter 17, problem 41. And so this problem gives us a parallel plate capacitor. And it doesn't tell us the area. In fact, it asks us to solve for the area. But we know for a parallel plate capacitor with area A, the electric field and those that subscript there signifies parallel plates. This is only true for a parallel plate capacitor. The electric field is equal to the charge stored in the capacitor divided by epsilon, which is a constant that depends on the type of dielectric you have inside the capacitor. But in this case, we just have air or vacuum, so we use epsilon naught. Which is a constant you have in your book, divided by epsilon naught, and also divided by the area of the capacitor. Now, if we want to solve for area, right? So this, we can manipulate this into area is equal to Q divided by epsilon naught area, and if we plug all these values in, so the charge we're given is 4.2 microcoulombs, and the electric field desired is actually, so it's 2.0 kilovolts per millimeter. We'll call it 2.0 megavolts per meter, because that makes more sense. It's 2.0 times 10 to the 6 volts per meter. So if we actually plug all this in now, we get 4.2 microcoulombs divided by epsilon naught is 8.854 times 10 to the negative 12th, I believe. And the area, sorry, oh, I've made a mistake. This, I meant to write E here. The electric field that we desire is 2.0 times 10 to the 6 volts per meter. And this works out to an area of 0.2, it's 0.23 something meters, so if we're rounding to two significant figures, it's 0.24 meters squared. Okay, so that's the first problem. The second problem is 17.56. And 17.56 is a bit more abstract. And there's two parts. The first part asks, suppose we have a parallel plate capacitor, same as last time, but we move, so we have an area A and a distance D between the plates, and suppose we cut that in half. And anytime you change something in a physics problem by a factor of 2, that should scream substitution. And in this case, we're going to substitute 1/2 D in for D. But before we can do that, we need to establish a few facts. So in general, the energy stored on a capacitor, I'll write it as U so we don't confuse it with electric field, is 1/2 CV squared, where V here is voltage difference, and the C obviously is the capacitance of the particular capacitor, and that can depend on a variety of factors, including geometry, but we know for a parallel plate capacitor, C parallel plate is going to be equal to epsilon naught A, or well, epsilon A over D, right? Because we don't know what the dielectric is in this case. So epsilon times the area of the capacitor divided by the distance between the plates. So if we plug this into our energy expression, the energy stored on a parallel plate capacitor is going to be, we can just as well write 1/2 epsilon A over D V squared. Right? Now that we've established that, what happens if we substitute, and I'll write in blue again, 1/2 D in for D? Well, we have that factor of 1/2 out here. And we put in a factor of 1/2 in the denominator. Those 1/2s are actually going to cancel, right? And we're just going to be left with epsilon times the area divided by D times the voltage squared. That is a messed up V, but you get the idea. So that the answer actually, because the question asked by what factor, the answer would be a factor of 2. Okay. Now, part B is related to part A. It asks how much work must be done to reduce the plate separation from D to 1/2 D. So, in other words, some external force is doing work on this capacitor to push the plate that distance, and we want to know how much work it'll take. And to answer this, we want to go back to our Physics 1 concept of work and energy, where we say that the work done on something is equal to the change in energy of the system, depending on whether it's the system that's doing work or the environment doing work on the system. That sign can be positive or negative, but in this case, that's simply, so it's U final minus U initial, right? Or it's, so that's U final, and our U initial was the 1/2 epsilon A over D V squared. So what we get is epsilon A over D V squared minus 1/2 epsilon A over D V squared, which you can see, so if you factor this out, it just turns into 1 minus 1/2 times all of that, or simply, well, so it's 1 minus 1/2 epsilon alpha over D V squared. But you can just as well see that 1 minus 1/2, I'm trying to get my eraser here, is just a factor of 1/2. So we're back where we started, which sounds a little confusing, but it makes sense. In order to double the amount of energy in the system and go from here to here, we had to put this much work into it, right? So we did 1/2 quantity epsilon A over D V squared of work, and we consequently doubled the amount of energy stored in the capacitor.